Okay, everyone. So this is a recording on processes and threads, Chapter 2. And we're going to talk about a number of different concepts related to how we can manage concurrent access by particularly threads to a shared resource, such as an internal data structure that multiple parts of program code may access at the same time, because they're all engaged in trying to do processes in parallel rather than sequentially try to improve program performance. And this, quite frankly, is a model that we have to be more aware of as we move forward into the future. The days of having single-threaded computer programs are largely behind us now, and we have to take advantage of the additional cores that are in CPUs because they're not increasing the speed. We don't have raw computational speed increases, so it becomes more important to be aware of these items. So that's what we're going to do here. All right, so central part of any operating system is obviously the process, right? And running software is sort of the point of it all. The oldest and most important abstraction in the OS is that of the process. It's a mechanism by which we can use for allowing what's known as pseudo-parallelism or multiple virtual CPUs. So pseudo-parallelism is this concept of making one CPU in the system look like it's a multiple CPU system by just rapidly switching among processes, right? So you give each process a certain quanta of time, and then you keep just rapid fire switching between them. It's kind of like, well, you watch a movie or a video, and that's really what you have is a bunch of individual frames that are moving at a sufficiently fast enough speed that to your eyes it appears as motion. And same thing with multiprogramming pseudo-parallelism is that we give the illusion, even in a single core system, of multiple processes running at the same time, because the switching between them is fast enough to create that illusion. A true multiprocessor system is something that has multiple CPU dies in it, or is multiple CPU cores that's in a single die. So in the past, probably early versions of this book would have assumed that there was a single core on a single CPU die and a single socket, right? Nowadays, we have multiple cores within any given CPU. We may have multiple dies, multiple sockets, but it's not as common. So because, again, that's a cost item to have multiple sockets and extra traces and bus wires and all that good stuff, right? So when we put more cores on one CPU, that's very large in terms of real estate CPU, and those processors have been kind of growing in size over the years. And that's fine. We'll just take it and its 1,000 or so pins of output, and we'll put it on a big section of that motherboard PCB. All right, and then obviously there's a process model that goes with all this, and that's just describing how the software is organized sort of into a sequence of sort of separate processes, single, multiple, a bunch of sequential processes, right? So here's A, it's running, and process switch occurs, right? There's one program counter. And then B is running through some code, and there's a process switch to C, and then a process switch to D. And really, think about it, process is just an instance of an executing program, including the values of its program counter, its other important registers, like stack pointer, sort of thing. In essence, then, because the OS does bookkeeping, where it keeps track of all those registers and the stack and other internal structures, files that it's opened, signals that assigned to it, so on and so forth. Really, what you have is a virtual CPU for each process that's running. For A, B, C, and D, you sort of have these separate ledger entries, right, that it keeps track of, and it switches between them. And to the core, the real physical core ones running on each of them. All right. So again, here we see 4 processes. In this particular process model, each with its own flow of control. That means its own logical program counter, right? So we have a logical set of values, and not necessarily the physical set is whichever logical set's being processed at that time. There's really only one physical program counter, right? Because there's actually one PC register part of memory, right? One dedicated cell of memory for the program counter for that, or word, or whatever it is for that architecture. And that's loaded with whatever whether we're running A, B, C, or D's logical program counter version. And then when it's finished, all that information is updated in the ledger. It's essentially saved, and then we kind of move on with it. Right? So here we can see over sort of a long enough period of time on the x-axis versus the process of these individual sequential processes on the y-axis, that only at any one time is anyone running. You see A runs, and then B runs, and C runs, and D runs, and then back to A, the B, C, and then D in a round-robin fashion. Right? So with all this, you have to remember, the process is the thing that is active in memory and has active state. It's dynamic in nature. It has a set of continually updated register values and stack space and live sort of memory and interactions by the user. Versus the program, which is just a binary blob that contains the code that helps the process to come to life. Right? It feeds it. Says this is how you exist in this world. So because of that, you have to think that it's important to program processes without trying to make assumptions about timing. It's generally a bad thing outside of a real-time operating system, where you can get guarantees about hard and soft time limits and the consequences of those being failed, and you can code accordingly to that. But in general, for a general-purpose operating system, where there aren't real-time requirements built in, you can't make those assumptions, right? So we have to do other things. Let's see here. Normally speaking, all right, most processes are not affected by the underlying multiprogramming of the CPU or the relative speeds of different processors, all right? And that's actually an important point, because think about a lot of our mobile devices. Nowadays they come with high-speed cores and low-speed cores, right? They're actually running at different internal frequency rates, and even within a single core, there's a base frequency, and then there's a boost frequency and a range of frequencies between those two that it can be at any given instance of time. So it becomes pretty complicated to keep that. It's not like the old PC days where you had your standard operating frequency of 100 megahertz or something like that. You could press the turbo button for working with an older program to down clock that core speed to say 33 megahertz or something, because there people did have assumptions in the old days about the speed at which things occurred. So early hardware attempt to work around some of those ill-placed assumptions was to have the turbo button, which does the opposite of what you would think it should do. Turbo button on those very early PCs should have probably been more called a compatibility mode button, or a time divider button, something like that. But that wouldn't have made much sense to people. But turbo button kind of gave the wrong impression, right? Anyhow, let's see here. Yeah, so keep in mind, a program is like a recipe. It's just a set of instructions for how things are to be done. Someone starts to bake or execute the program. The process of reading the recipe, getting the ingredients, and baking kind of goes from that point, right? And then an interruption is having to switch to something else. It's a context switch, right? And that's what we see between A, B, C, and D here. It's kind of like the baker is working on the main course and has to switch his or her attention to, I don't know, working on a garnish or a side dish, or making sure that the salads don't get too chilled. I don't know what it could be. It could be something, and then has to come back to it later, right? Same thing with computer science. You have a process, or a computer. Let's look at a computer scientist. The book kind of mentions this. You have a computer scientist. In this case, my daughter would come in if she got stung by a bee, screaming her head off, right? And then I have to deal with that much higher priority issue of my daughter being stung by a bee than dealing with whatever my current work task is, right? So I had to go from a lower priority task to a higher priority task, in essence. And you could maybe perhaps see in some contexts how these might be higher priority tasks, right? And that's a notion. Different operating systems will have different ways of dividing the priorities of processes. Some may not even have a notion of of prioritization. Some do. Some have a few levels. Some have upwards of hundreds of levels of priority that you can utilize. And then obviously a single processor can be shared among several processes. Use some scheduling algorithm to determine when to start and stop working on various different processes. Program is really something just stored on disk. It's a blob. It's not doing anything. It's static. It's just zeros and ones that are permanently stored, right? And obviously this looks uniform here, but that's not the reality of it. If you just even look at threads in a Java program, you're going to not see that sometimes a pattern may emerge depending on the type of code that you're running, and it has a periodicity to it, but it's not guaranteed, and often you'll see things kind of shift, or things not occur exactly on that frequency, although it looks like the general pattern, if you're to visualize it like this, is kind of kept, more or less, but enough variation for it to not be uniform and not reproducible, based on everything else going on in the system. Alright, so when we talk about process creation, right, and there's 4 ways in which processes really get created. The system boots. So on a Linux system, Unix system, init runs, init goes through a boot up process. It's starting off all sorts of different server processes, daemon processes, getting that system up and running, getting the hardware connected to the software server, instances, user services, that sort of thing. Just getting the system to the point where it can be utilized by clients or by users or whatever the case may be. Background processes that stay long-term service requests are known as daemon processes. Like looking for new incoming mails, right? Like you have Outlook open, and periodically pulls your email server to pull down new messages, right? The second way we can do this other than system initialization is execution of a process creation system called by a running process. So you have a shell environment, user decides to do a list or decides to concatenate some files together, maybe search on a phrase with a grep, whatever. Each of those kind of individual different utilities or the combination of utilities through a pipe will generally lead to the shell creating those processes, doing the fork and doing an XQV operation to replace the current shell program with that listing program or that grepping program or that concatenation program. And then the third way this can happen is the user requests a new process. Double click on an icon in Windows Explorer, some sort of other GUI shell environment or a GUI desktop environment that creates that process, like a text editor or something. And then obviously we have initiation of a batch job. So a currently active process can execute, say, create process system call and directly tells it which program to run, right? In a sense, right? Generally speaking, number 4 would be more like a cron tab, or a cron tab. A cron tab would generally be the mechanism by which you do it, and then it would start up maybe a script file, batch file, something like that, and it would start with a number of processes in a sequential order. It may have a bunch of files in a special directory. It has to process with one process, right? And it would do things like that. Keep in mind, Unix may use fork and execute v. Windows will use create process, or one of its 32 different flavors. And generally speaking, in Unix, memory images from the parent to the child are the same, right, until XQV is executed, and anything else, it kind of stays the same after that point. There's a copy on write notion, so that as the child starts to do things, especially if you don't replace that image, that's unique to that child process, then certain pages of memory are going to start changing, and it'll be unique to that child versus the parent. So as long as everything else stays the same between the parent and child, and you're not changing pages of memory out, they'll stay the same and improve efficiencies in terms of memory utilization across processes. Windows doesn't have this notion of parent-child sort of relationship. It's just process creates process. And it's its own thing. And with create process, it combines those two calls. You have to specify what program code to run in that create process to generate that unique process. So. And here are the system calls, man section 2, all right. And here's the fork create a child process, right? And you just have to just call fork. There's no parameters, so it's void, right? Executes VE. This form, there's other versions of execute that suffice for variations. But basically, you tell it where the program is, what arguments to pass to the program, and then if you want to give it a set of environmental, an array of environmental pointer values that are of interest to it. Generally speaking, it's not something I normally use, but it's there anyhow. Okay. And then here would be a excuse me, create process on Win32 API systems, and it's pretty complicated because again it combines those calls together, plus it deals with security issues and other things, right? Create a new process in its primary thread because all processes at least are a single thread. And it runs in the zero query context of the caller. All right. So you can tell it to implement another user in the context of doing the call, right? And I guess it would be part of its environment specification. No, actually, I know it says right here. So if you want to do it in context of another user, you would use the create process as user. Create process with log on W. All right, so there are variations of that. And then down here, there's 10 parameters. Right, the program to be executed, the command line parameters to feed that program, various security attributes. All right, that control whether open files are inherited. Let's see here, priority information. See here, specification of the window to be created for the process of any, and sort of a pointer to structure in which information about the newly created structure is returned to the caller. So, yeah. And then programs run, they do their thing, and then eventually you come to an endpoint for a given process. Those endpoints are either sort of someone exits the program, right? And the underlying program calls exit in Unix or exit process in Windows. Number 2 method is there's an error exit on the part of the program code. It finds a situation that it doesn't think it can reasonably recover from, right? So it issues the exit with an error code return. It's a graceful exiting of the program, right? It doesn't like crash and burn. Number 3 is a crash and burn. It's a fatal of error. It's an involuntary termination of the process. And it's like a divide by zero sort of situation, right? Runtime errors, basically. And then number 4 is it's killed by another process involuntarily. So if I'm at my shell, and I don't know, I see Civilization 6 is locked up when I go to start a new copy of it, because the old one didn't terminate properly, I could do sudo kill-9 PID of the hung process. In that case, that kills that off, right? So again, I mentioned Unix has a notion of a process hierarchy. Windows does not. Everything descends from a init, essentially, in terms of parent, child, grandchild, blah, blah, blah. And then a process and all its descendants will form a process group, right? So process hierarchies in Unix aren't really like a sort of like a cow. They're more like a hydra, right? So there's multifaceted things because new processes can come from any point along the hierarchy at any time, so it becomes more hydra-like than cow-like. So, and then there's interesting things like, well, what about singles, right, which are software-based interrupts? Do they go to all the processes in a group, just one process in a group? Generally speaking, you have to have a process that registers with interest in getting that signal, right? If another process gets it, its default action is to kind of die, but it may also need to set itself up so that it just ignores it as well, or actually responds to it. So catch, ignore, or die are the sort of the actions it can handle. And I already mentioned initialization at boot. So reads files need a number of terminals in this example. Forks a terminal per terminal. Login terminal, if it's successful, then it'll start up a shell with XQV, and then all the processes there belong to a init. Right? So there are three states that a process can be basically in. As running, they're actively using the CPU at that instance. They are ready, they are runnable, temporarily stopped to let another process run, and blocked, alright? Unable to run until some external events happen. So there's only one process that can be running. There may be others that are ready to run, and there's nothing that keeps them from running. They're not waiting on some I/O. They're not waiting on user input. They're not waiting for print queue to be done so it can send the statuses back to user and whether something printed or not. They're just there. They're ready to go at an instant. Number three is something external to the system has to happen before it can go back to ready. Alright? And then once it's ready, you can go to the run, and at any time you're running, it could just use up all its current time and go back to ready, or it could actually go to block depending on its need for various resources and system calls that are blocking that it makes, that sort of thing, right? So yeah, here it is. If I'm running, I can go back to ready if I use up all my time. I can go back to running again if there's nothing else going on. Or I can be running, I can go to block. Once the I/O or the system call issue that calls the block is resolved, I go back to ready, and then at some point I'm put back into a running state. And again, here, if I were to look at my processes and just look at the IDs and the states and the commands, I notice here that I have some that are interruptible. Sleeping, I'm waiting for an event to occur, like init, read-only, read-only. Here's one for the shell. T means that it is stopped either by a job control string or it's being traced, like sleep, right? You issue a sleep call and then you put sleep. And then R is the thing that's running, which at this point in instance when it's listed was the process listing command. I can actually just BG that process as well and put it into sort of a that S state here from being running, right? So I could do that, background it to sleep, and at some point it could get a signal, go back to running again, right? And then if I'm running, I can get an uninterruptible sleep. I put me at state D, and then I can get woken up again to go back to R, and then here's the state, interruptible state like sleep, right? It needs a signal to come back to R, and obviously if I go to Z, this is where a child would exit, but the parent hasn't acknowledged it, so it becomes a zombie. Alright, so again, here's another example of that. So once the backgrounding occurs, you can see what I do to get it to that point. I probably piped something to, what did I do? Oh, I sent the phrase yes to dev null. I have it right here. So I can do something silly like just type the word yes and send it off to the bit bucket in the sky. And when I do that, it probably should be something that's like state T, but more than one core. I can get a schedule on one of the cores, and now it's in a process list is on another core. And it's funny because it's there, and because of this Windows subsystem layer, I can actually get a process here that's called the yes process, even though it's really just a word and it's not really a program underneath it per se. It's just something that's nonsense. But Windows doesn't seem to really understand that because the Windows subsystem layer is taking it, which has CPU utilization, all this other stuff, which is kind of funny. So it's just an example of seeing a process in a block state, and then we'll stay in the running state till it's terminated, right? There's things that you can do. I'm not going to show it here right now, but you can write a shell fork bomb that'll just keep generating processes off the shell without XQV and eventually crash the whole system. That's something I like to run because it can also cause your file system daemon to crash, and that could cause file system corruption. So And the code looks really weird and short and obtuse. So here is the sort of the lowest level of the operating system. There's a scheduler. There's a variety of processes that kind of run on top of it from 0 to n-1 there. And all the interrupt handling details of actually starting and stopping the process are hidden away in what's called the scheduler down here, which is really not a whole lot of code. Schedulers tend to be pretty small pieces of code. And the rest of the operating system is kind of nicely structured into various process forms, 0, 1, and -1. And then to get the process model from daydream to reality, a process table has to be created, right? So that's task answer kind of shows you elements of a process tree, kind of visualize. You do top or htop in Linux systems, you get the same thing, right? You get sort of this visualization of what could be in the process tree. It doesn't show you everything. You can tap keys and make things more or less show up, but it's still sort of a snapshot and and not everything that is maintained underneath. And you basically have one entry per process, right? So process control blocks, PCBs in some contexts. And then important info on process state that is stored, right? So to do the bookkeeping of process, you model the model. The OS keeps a process table. It's an array of structures. It's one entry per process called the process control blocks. Associated with I/O is a location near the bottom of the memory called the interrupt vector. All right. So these PCBs are put in the memory somewhere. They're placed near the interrupt vector. The interrupt vector is just, hey, here's the set of assignable interrupts, and here's where you go in operating system code to run a given interrupt routine for a given numerical interrupt as it's singled by a GPIO from some pin attached to some peripheral device or something on the main board or whatever. And so you keep program counter, status word, right? That's a thing with all the bits about the state of the program. There's been a 0 flag, trigger a negative flag. You know, there's been a jump recently, you know, conditional or unconditional, so on and so forth. Priority of the process is scheduling parameters. Process idea was assigned when it was created as a child. Who its parent process is, right, in terms of its ID. Time when it was started, how much CPU, time has it utilized, so on and so forth. And then there's some memory management things that point to text, data, and segments. And then obviously for file management, root directory, working directory, file descriptors, so on and so forth. And then the skeleton of what happens at the lowest level of the operating system when like a hardware interrupt occurs. So hardware stacks the program counter and other important pieces of information away. It loads a new program counter from the interrupt vector. Assembly language procedure saves the other registers for the currently running process. Sets up a new stack based on use of the interrupt. And then the interrupt service runs, typically reads and buffers the input, and then it returns to the assembly code. The assembly language procedure starts up the new current process. So it is possible to kind of model multiprogramming, right? Having some, looking at the parts that are used in the CPU, which parts are doing the I/O, which are just kind of sitting there, right? Idle, waiting for something to happen. And CPU utilization can be improved in multi-program use, right? So you can have offload sort of I/O activities through controllers and have some smarts to them, and have the CPU actually work on code that's ready to run with various instructions. That's great, right? And this program chart here kind of looks at CPUs from a probabilistic viewpoint, right, using a binomial distribution. Either a process is running or it's not. And the degree of CPU utilization is 1 minus P, or time spent for waiting for I/O, raised to the n, right, because you have n processes across which to spread this. You can't have multiple process running. Let's go to that after a process I is done waiting, it has to wait for the CPU to free up. So it isn't always an instant switchover anyway. So processes and wait and run states are not really independent per se. You could get a more accurate model than sort of this binomial distribution, right? You really bring in queuing theory and kind of look at all the nuances of this stuff. You could use the Poisson distribution to model things. More complex, but it's probably a little bit more accurate. But generally speaking, this is generally good enough. So you can kind of see the degree of multi-programming you would need to get to certain levels of weight, right? So obviously, at 80% I/O weight, you really need a lot more processes to kind of increase that CPU utilization. Right? At 20%, you know, it kind of scales up pretty quickly, right? And then we'll move on to section 2.2 here. Okay, section 2.2, threads. All right, so the tradition has always been single process, single thread of execution. Today we tend to separate our code bases into logical sections, and we assign a lightweight unit of execution to each of those logical units, and we call those logical units threads. So one thread to capture keyboard input, one thread to write a file, one thread to check for incoming values on a buffer, one thread to do this or that, right? Basically, many processes are threads, right? So and threads tend to be associated with major portions of a program's operation. And you could do very fine-grained threading or very coarse-grained threading in your application as your particular needs dictate. So why? Basically, you want to allow multiple independent sections of the code to run at the same time and coordinate their activities. You want to allow data without dependencies to be processed in multiple chunks at the same time without having to go in a sequential manner. You may want to have one thread that does I/O, another that does CPU to kind of get concurrent multiprogramming. You may want to give parallelism to the process, not just between the processes. Okay? And Java has one, for JavaFX, one thread for doing the GUI, another for main execution of program logic. In fact, in Java, any long-running process like network communication, it has to be done on its own thread. So, anyways, let's see here. So, again, here's a word processor with 3 threads: keyboard, disk, and current contents of what's in the word processor. And you could have a separate thread to each of those. Right? Keyboard taking input, disk to write out changes to the Word document in the word processor, and then obviously a GUI that renders we seek rendering of the environment itself. Right? So there's that one, the word processing document. Keyboard take input, disk to write out changes. So a traditional operating system processes an address space in a single threaded control. We tend to have multiple threads of control in the same address space running in quasi-like separate processes. Otherwise, things would be constantly blocked, waiting for anything to happen. You get a keystroke, you update the document, change out the disk, so on and so forth. So threads are many processes. Again, it helps with multiple activities going at once, some blocks from time to time, so it's good to be able to switch between different sections of code within your program living as a process. Right? Of course, you have to be mindful of how to build algorithms, design your overall architecture of an application. When using multiple threads, you want to decompose in such a way that multiple sequential threads can run sort of in this quasi-parallel fashion, right? If you don't have true multiple cores and all that sort of thing. You can switch not only between the processes, but within a process among the threads of execution. And threads are lighter weight. They can be created and managed, especially created, 10 to 100 times faster than dealing with individual processes that could be working on different parts, right? And it's possible to get faster performance gains within one app by multiprogramming the CPU and the I/O among the threads, right? So that you can always try to get some section of code doing some useful work within the CPU core when it's scheduled for processing, right? And threads are useful in systems with multiple CPUs. Or cores or real parallelism is possible. It's even a more advantageous thing to have. So pretty much the thread will interact with the user. In this case here with this figure, second does the backups periodically to disk of changes, and then the third will reformat the document. Right? So you can't really do these as separate processes because you would need a shared section of memory in which to do this, and that's kind of really hard to coordinate. Okay, so just imagine a multi-threaded web server. So typically speaking, you'd have a server process. What it does is it serves up pages. Either those pages are available in a cache and it can directly deliver those back to the client, or it has to go out the disk, read the file into memory, cache it, send it off at that point. So typically speaking, in a modern web server, used to be you'd spawn off a process for every request that would come in the very early days of the web. That was really, really resource intensive. They don't do that anymore. So what you do instead is you have a pool of threads, and they're dispatched one at a time to serve various requests up to some maximum number it can support. And the unused threads are idle or blocked. They're worker threads. And as each request comes in, worker threads woken up, takes that request, looks for that request in the cache, or goes out the disk and pulls it in for sending back to the user, and then caches it. And then once it's done that, it goes back to the pool of newly available threads. Right? And that's pretty much all that goes on there. All right, here you can see how this might work, right? So here's the dispatcher thread, get the next request, and it requires really sort of a dispatcher thread and a worker thread system kind of working in tandem. So there's one guy that's sort of the traffic cop, and that's what the dispatcher thread is. And he gets the next request whenever it comes in. There's probably some network block going on here, waiting for something to come in. And then when it does, it hands off that work and that particular buffer to that working thread. Worker thread basically waits for, there are a bunch of these, they wait for work, they get the work at some point when the request it gets handed off to them. And then they look for the page in the cache. If it's not in the cache, they read it from the disk and put it into the cache and return the page. And anyways, you need to obviously have appropriate data structures, as highlighted by Buff here, that support this. There's a non-blocking version of the read system call. An approach could be that you have only a thread examine the requests that come in, and then call read with callback. And then at the point of the callback, one of those worker threads then goes over, reads the file in, caches it, and sends it back. A non-blocking version of that with callback. If you have noticed it doesn't have sort of a non-blocking read, well, then it sits there while it's waiting for the read to complete. And then it goes off and completes the request. So you could have multi-threaded and non-blocking I/O as well, right? Dispatch off immediately. It could do a non-blocking I/O. It could work on another request and deal with that. If it's in the cache, any other request is likely to be in the cache. If not, it could do other non-reading blocking reads, and then services in a queue. It can get more complicated, basically. So. Alright, and here is the models that we could use for constructing a server. There's a thread model, there's parallelism, there's potentially blocking system calls, there's a single-threaded process, no parallelism, blocking system calls, and a finite state machine. There's parallelism, non-blocking system calls, and interrupts, right, for when the reads finish and have to notify that those are done, right? So, they're all three very interesting models, and they all have certain strengths and weaknesses attached to them. So, in general, blocking calls are easier to implement. That's why you're going to find them more often than the non-blocking calls, right? because they require additional parameters to return the call when some event occurs, and straight transition take place. So. But you can still get parallelism with blocking calls. It's just that it's not as robust, I guess, as non-blocking calls. So. All right. So in terms of being able to, it is possible to work through getting the Linux process descriptor. You can look at the Linux source code tree and do some things. I'm not going to deal with this right now. I'll come back to this maybe in a separate lecture so I can walk you guys through this. So I'm going to move on. So the classical thread model has sort of these independent concepts of resource grouping and the execution of threads, right? So a process group brings together multiple resources like an address space, text, and data that all the threads can share. And then things like open files or child processes or alarms or single handlers are by a per thread basis, right? So the thread has its own PC program counter. It has its own set of registers in a ledger type structure, and it has a stack and execution history of 1 frame per procedure that's dedicated to each thread. So threads are scheduled for use by CPU, either by the kernel or by some user threading model that we'll get to. Multiple executions in the same process environment, different than parallel CPUs running multiple processes at the same time because they all are heavyweight and everything is independent to each process, right? And then you're forced to use some message passing thing to communicate, or use a shared memory, some other mechanism. So here's sort of our classical thread model. So let's see here. Okay, so what we see here is a way in which a thread of execution can occur. On the left side, we have 3 processes, each with a single thread in its process space. All right. And so here's a thread, here's a thread, here's a thread for processes 1 through 3 in user space. And obviously, we have the kernel down here at the bottom for both of these. And then over here, I have one process with 3 threads, same address space, right? Because they're all together within the same process. Remember, threads, they have their own separate copies of program counters, so the registers, their stack space, 1 frame per procedure in terms of its current calling sequence, its stack trace, and its own file handles and singles and that sort of thing. But what it shares with the process is that of unified access to the address space, so that all threads can reach things like common globally scoped variables, data structures, that sort of thing. So these threads execute in a process. They're really different from a process, right? They're essentially, processes are used to group resources together for execution on the CPU, and you allow multiple executions to take place in the same sort of process environment, right? So this is essentially fine-grained parallelism here, right? Threads are called lightweight processes, and we have this notion of multi-threading, which is allowing multiple threads to run in the same process. Right? Yeah, so same address space, same shared global variables. One thread can't wipe out another stack, though. So there's that, right? Whereas with here, you would have to provide coordination mechanisms for one process to talk to another, right? Remote procedure calls, shared memory space, writing to a common file, something that's complicated and efficient. All right, so here we have, here's the per process items. Address space, global variables, open files, child processes, pending alarms, singles and single handlers, pending information. Here's your per thread items. Program counter, register, stack, state, that sort of thing. So, actually, yeah, singles are kind of a per process basis, not a per thread. Sorry. Yeah, and then you could group them together and set them up to respond as needed. So, all right. And obviously they share data, so they would share open files, that sort of thing too. So. And there is no protection between threads, right? Because it's impossible and it shouldn't be necessary, really. The whole point of it is to kind of have the ability to kind of easily get at data that you need for processing, but then do it in a parallel way. So different processes could be from different users. These processes should normally in a secure environment be considered to be hostile to one another, right? Because they may have different usage rights, that sort of thing. REST threads are kind of all assumed to be started from the same instance in time, right? They have all sort of the same goal in terms of how they're running. So they can assume to be working in a cooperative manner, right? Not an adversarial one. So here we go. Each thread has its own stack. So here's thread 1 stack, thread 2 stack, thread 3 stack, right? One frame per procedure, essentially, right? Threads can be in the same state of processes, basically running, block, or terminated, and variations in between. Running thread currently has the CPU and is active, whereas a blocked thread is waiting for some I/O. A ready thread is something that is scheduled to run, has nothing to keep it from running, it just hasn't been put into the CPU core. So if procedure X calls Y and Y calls Z, then while Z is executing, the frames for X, Y, Z will be on the stack. So it could be one of these, right? And generally speaking, different procedures will have a different execution history, right? That's why each thread needs its own stack. So when multi-threading is present, processes usually start with a single thread present. Each thread has the ability to create new threads by calling a library of procedures such as thread create. In thread create, you give the name of the procedure for the thread to begin its execution, right? So there's no separate execute thread VE or something like that. And generally, there's no parent-child relationships with threads, but there can be groups or pools of threads that serve some common purpose. So here we can see common calls in the POSIX threading model, right? So POSIX is our set of common calling system call conventions that are used across different flavors of Unix and Linux, and there's a section that deals with lightweight processes or threads on different Unix or Linux implementations. So we have a thread creation system call, a thread exit, a join, where you wait for a specific thread to exit, a yield, where you decide a thread can make any more progress and you want to have it give up its remaining quanta of runtime to another thread. And then these init and destroy attribute values are about creating attribute structures and removing attribute structure. This is all about changing properties of the thread during its runtime. Right? So here's an example of how we could create 10 threads. And I mean, I could run this code. I posted an updated example with a makefile on the website that you can utilize. I just kind of create some. It can kind of sit there. It can kind of exit. You can vary this code a little bit. It is what it is. So pretty much you have a standard C program and you can have how many threads you want. So a for loop from 0 to number of threads. You basically do pthread create. Based on the counter value, right, because you're creating an array of threads. You tell it to start at the print hello world routine here, and I'm trying to think what that parameter is there. I'd have to go back and look at the system call on it. But anyway, so yeah, basically it's going to generate 10 threads. Each of them are going to start this print hello world, and it's a parameter list into the procedure. So yeah, it needs it as a void pointer, so hence casting this to a void pointer. Newer C implementations require a pointer to a primitive data type pointer, and then that is double converted to the void pointer for it to build without yelling at you. Anyways, so yeah, so you start this routine, you pass to it I in this case, which is its thread number, all right, different from its process identifier. And it prints out that hello greetings from thread and prints that as its thread identifier, TID, exits. And that's pretty much it. And then once it's done, as it does each of those, if at some point it came back with a status of not 0, it means an error state, and something bad happened, you print its error code and you would exit. Like maybe ran out of bookkeeping space to create additional threads. I don't know, maybe something else was running on the system that just kind of ran away with everything. Right. So, in contrast to doing, well, there's really two models of how you can do threads. So you can do user-level threads packages where the kernel is unaware that there's a threading system in place, or you can do a threading model where threads are maintained by the kernel, or you can do something that's in between the two models. So user mode threads can be implemented on a system without support for threads, and that's user mode threads, user level threads. And it can be implemented using a library, and it's still done this way in some operating systems, right? So in this case, each process needs its own private thread table, and that's kind of what's shown here on A. So here's a thread table for this process with some threads, and then here's another process with some threads and its own process table, or thread table, and so on and so forth. So you have the kernel has a process table, but it has no awareness of threads, right? So that's all it has. Whereas on side B, there's a threads package that is maintained by the kernel. So there, you don't see a runtime system in each process with a thread table. You just have the thread table as part of the kernel data structures. So, and then the runtime system is the thing within a process that handles the different threads of execution, switching between them, and doing all the bookkeeping. And it's always trying to keep something active. So when it is a process is scheduled by CPU to run, there's something meaningful for it to run, and won't immediately block and have the CPU switch out to something else. But, you know, this is important, this whole thread table maintained by this runtime system and user level threads package, right? So when a thread does something, it may cause it to become blocked locally, like waiting for another thread to complete some work. It has to run a runtime system procedure. It checks to see if the thread must be put into a blocked state. It kind of stores its registers into the table, looks in the table for a ready thread or thread in the ready state, right, that can run immediately without anything else being done, and loads its machine register values from the ledger into the actual physical version of it. Eventually, right, it could go into a sort of a virtual CPU thing, and then because the kernel doesn't know about threads, it could at some point oh, it has this program counter now and has some of these other register counters because that runtime system updated. I guess I should use those values when I'm working with this process. And it just goes forward with that. So. And then pretty much as soon as the stack pointer and the program counter have been switched, the new thread comes to life and can begin automatically under a user level threads package. Switching threads is faster if you keep it all in user space. You don't let it have to do the trap into the kernel and do the operations there and then go back, exit the trap, back into the user space. It's a lot quicker. However, they have to worry about this blocking calls in the user level threads package. Sometimes these systems provide sort of a select call that you can make, and that basically determines whether or not a call is going to block and lets it take appropriate action. Now, this requires you to have jacket or wrapper code placed around system calls to help to select to test when it's safe to do blocking. So it makes sort of the envelope of these system calls very ugly kind of to look at, but it's what you have to do. The goal is not to have a single thread basically issue a blocking call under a user level threads package. Like a read that would block the whole, because if it blocked that whole process, and then it's just going to switch something else, and it's not doing any more useful work, and it appears to be more sluggish to the user. So, yeah, jacket wrapper code just isn't elegant or efficient, but it's necessary. Right? There may also be situations where there are page faults, right? So we talked a little bit about this in computer architecture. We'll talk about it here. Program code is often divided up into multiple pages, right? Processors are loaded with a virtual address space, right? Where it looks like it has access to the whole addressable memory of the system, right? Then, as that program runs, parts of it are actually placed into the real physical memory, but only pages at a time of it is. if at some point it goes to execute the next instruction or look for a piece of data, and that isn't currently in one of those pages, then a page fault occurs. It has to go out the disk and read all that information in. At that point that it happens, it's hard because the runtime system may not be able to catch this, so it can't swap the threads and the whole process into blocking, but they may be able to and keep it going, right? Until that CPU is able to read in that. The physical CPU is actually able to read something to actual memory, and then it can switch back to it and run those instructions or get access to that data. So, so also when the situations occur that the runtime system can get that thread out of, it needs to have a mechanism for that thread to yield themselves. And again, even with the clock mechanism, it can be messy, right? We depend on threads and these user-level threads packages that give up the CPU to yield themselves, and that sort of cooperative model is hard to enforce. It's hard for it to always operate efficiently. If it turns out that, and that's kind of how Windows 3.0 was. It was ran under that kind of model, and it was a lot more error-prone. Right? But in any case, if you keep everything in the kernel, then once the trap's been done for some other thread, it's easy enough to have the kernel make that check and then swap threads in and all that good stuff, right? And so with kernel mode threads, right, creation or deletion requires a kernel call, table, and kernel with register state and other information. Expensive because you got to jump into the kernel, jump back out, right? But then you lose a lot of those other types of details and complexity. So basically, with threads, less info is kept on a per thread than with the single-threaded processes. So it's sort of a subset of the normal process state. Blocking calls cost more runtime of a system procedure, so OS can read a thread either from the current process or another process. It can actually look into those individual threads, not just work at a process level. So yeah, there's that initial cost, but then it can also be a little bit more intelligent about how it does the switching. So you may gain later on because of that. And really speaking, you don't need any new non-blocking system calls to implement kernel threading, right? It handles page processes without issue, right? Because it just go out, grab thing from the page from the disk, put it in the memory, and keep going. Whereas user-level threads packages can't handle that. Thread management calls are sensitive calls, so they're expensive. And there's other issues like how do you handle forks, copy all threads or just the main. Generally speaking, we copy the one thread, right? And then to kind of reduce cost, thread pools are kind of used. Remove threads are marked as not runnable if need be. So the hybrid model is basically a user can specify how many user threads there are in a system, and then some of those user threads can be mapped onto a smaller subset of kernel threads. So the kernel has its kernel threads, it manages those, but the user can overlay that single kernel thread or several kernel threads with multiple user threads, and it has its own runtime system. It kind of manages those threads within the context of that single kernel thread. Kernel can manage those kernel threads within, and you kind of get something that's in between, right? So it gives some benefits from both systems, some costs from both systems, but it can be useful in certain cases. I wish I had more data on where each of these models are good to use, but I really don't. So schedule activations with user threads is so kind of our goal is we want to mimic the functionality of kernel threads in these hybrid systems. We want to avoid special non-blocking system calls because anything that because any call into any system call requires a trap into the kernel, right? So you jump into it and you go back there, so there's an efficiency issue. we want to make sure we can always schedule another thread that's ready on a blocking system call or a page fault to run. We just want to make sure that whenever something comes that stops the forward progress of that thread and turn the process, make sure we can get another thread up and running without doing a context switch, which would also be sort of a jump into the kernel and back. So kernel assigns a number of virtual processors to each process, lets the user space runtime system kind of determine how to allocate the threads to these virtual processors. The user process can request more virtual processors. Kernel can take them away if need be. Process could yield them, I guess. Kernel will know a thread is blocked, right, because of the trace of system calls into the kernel, parameters on the stack, that sort of thing, right? And there's this notion of an up call, right, that can be triggered from the process, right? Which is kind of the runtime system within that process of a known starting address and sort of like a single in Unix. So there's also this notion in some systems of pop-up threads. Right, so that's a thread that's created in response to receiving a new message to handle it. And generally speaking, pop-up threads tend to be brand new threads, not recycled threads. So there's no history that has to be restored. It's fast to create, keeps the latency low. But you have to do some advanced planning for it, right? Which processes to run it and all that good stuff. And it's faster than a kernel process, but bugs are likely to remain in the app or system. It could tie it up, right? So, the final sort of section here is, if you have an existing single-threaded application, it's hard to make it multi-threaded. You have to really think about where it makes sense to take where to divide up the different parts of the code. You have data that where it makes sense you can divide it up, things that are independent of one another. Sometimes you want to have multiple threads in one section of code that works over a data structure. It can be divided up into sections. If it can, great. If not, then that's kind of hard to deal with. And also the use of global variables and data structures can really be something that's hard to kind of deal with and program and work around with the bugs on. So you have to really worry about this global variables. Anything more than one thread could touch is basically something you have to protect. And the way you go about it is either you prohibit global variables, which isn't very practical, or you assign each thread its own private copy of global variables, and you kind of create new scoping levels. Okay, so when making single-threaded code multi-threaded, we have to be aware of globally accessible variables. All right? And the ways we can protect them is allocate a chunk of memory for the globals and pass it to each procedure and thread as an extra parameter behind the scenes. It's ugly, but it works. The other alternative way is create library procedures, create, set, and read global variables so that they're protected, so only one thread can access and manipulate that variable at a time. So those are two ways of doing it, and that second one is the way we'll be looking at in a little bit more depth in upcoming classes. Okay. So it's important that system calls are not generally designed to be reentrant. That means we can't be inside of a system call and have it call itself again. Right? It's hard. It limits parallelism. Right? In general, memory allocation chains like malloc are difficult to rewrite for multi-threaded operation, just due to the interruption of bookkeeping activities by potentially another thread execution, rendering the entire purpose of doing memory management with malloc kind of mute. So a different solution is that you could have the procedures each have like sort of a jacket that sets a bit to mark the library as in use, and any attempt for another thread to use that library while a previous call hasn't been completed is just blocked. Which works, but again, it eliminates parallelism, right? And that's just the way it is. Singles are, remember, are thread specific. Some of them are, some aren't. like alarm versus keyboard interrupts. So alarms can be made thread specific. Keyboard interrupts really can't be. There has to be, any thread could be interested in a thread, right? One thread could change, I'll share the same address, the single handle for other threads. Generally, since they're all cooperating, you hope that doesn't occur. Generally indicates the programming here. Or a thread may want to capture Control C, another may want to X. So it's really hard to have singles work with threads, right? And that's sort of the point of this whole slide here. And there's no easy answers to it, and how different systems respond to singles in different ways with different threading models. All right, and then stacks. Kernel might not be able to tell if one thread stack overflows. Each thread really needs its own stack. So, and these are sort of the things that there's ongoing operating systems research into. So it's beyond the scope of this course and really beyond the scope of sort of my comfort level. So, all right. So that brings us to the end of section 2.2. The next section is on inter-process communication and all different mechanisms that can be used for doing that.